So hello everyone again. Now I'd like to give a summary to the projects I have involved in the past few years. Basically, my research includes two parts. The first part is advancing the Green's theorem wave separation method to deliver new and more effective methods for those essential pre-processing steps. Among different progresses, I focus on three topics. The first one has been described earlier today, to get the actual recorded data deghosted with a non-horizontal acquisition surface. So the second part, we extend the Green's theorem wave separation from offshore to onshore for ground rule removal for ghost removal. This is a land data example. As you can see, the ground rule actually dominates the energy. The separation of a ground rule without damaging the reflection data is a high priority for onshore processing. So the current method, like the linear filter method, can remove the ground rule, but often at the expense of damaging the reflection data. For whatever your processing objectives are for the reflection data, multiple removal, depth imaging, you do not want your reflection data damaged. So this work is providing that essential prerequisite. So firstly, we developed the elastic Green's theorem wave separation method, which is able to separate the ground rule together with ghost out from your reflection data. And later, an example will show you the performance of this method. Well, considering this complete algorithm has a high data requirement, which is not easily to be satisfied today. So in a further step, we develop a simplified algorithm with a significantly reduced data requirement. In comparison with this complete algorithm, this simplified one still provides you the effectiveness and the usefulness. So now let's look at what the complete data requirement is and what the less data requirement is. This is the elastic Green's theorem wave separation algorithm. As you can see, the output here is the reflection data without ground rule and the receiver side ghost. So overall, we put the source at the air Earth boundary. There is no cell side ghost. We skip all the detailed derivation here, but just like to remind you one very important point here. This is not the traditional linear filtering method for ground rule removal. This is a wave theory derived method to directly predict the upgoing reflection data. In fact, there is no damage on the upgoing reflection data. Now, to achieve that, you need to have both Green's function G0 and its stress tensor in that homogeneous elastic reference medium, and both of them have analytical form. They are actually high dimension. It's a tensor. It's here, and second, you need to measure both the multi-component displacement U and the multi-component attraction T. Well, now you can see people usually measure the displacement, but not attraction. How to compute that? Well, by using the Hooke's law, you can actually compute the attraction following this algorithm. Two very important messages here. First, you have these lambda, mu, they are Lamé parameters. Therefore, to compute the attraction at a specific point, you need the local Earth property there. And the second point, you have these derivatives of each component displacement along different directions. They are required for the computation of the attraction. While the horizontal derivative can be computed by using the neighboring geophones, but to compute the derivative along the vertical direction, you might have an extra acquisition surface, which is really a high demanding acquisition. But nevertheless, it's natural for us to see how this algorithm performs when you satisfy the data requirement. We give U, give T, see what happens. Next, we show you an example, give everything is needed. This is a very simple model. You have an air half space and then the two-layered Earth. The source as a force vector is acting on the air-Earth boundary, and the receivers are buried at 100 meters below the air-Earth boundary. Now we will generate both Ux, Uz for displacement, Tx, Tz for the attraction, because all of them are asked by your theory. Next, I'm going to only show you the result of wave separation result along the x direction, but to compute that, we need to input all these terms to the wave separation algorithm. Now, with this model, you will have this total UX. Here in this data, you have a direct wave, you have a relay wave, you have these primaries. Again, this is the elastic wave field, so the wave will contain different PS combinations. Therefore, you have different events here, even though there's only one interface below the air-earth boundary. In addition, you have these ghosts. So for simplicity, we do not include the multiple here, but this algorithm does not have that limitation. Now let's input this UX together with UZ, TX, TZ to that wave separation algorithm. We will get this wave separation result, the primary event, which is the outgoing reflection data. Flip back and forth, you can see even though the interference among different events are terrible, but this wave separation algorithm can still provide us very satisfying result. Now you can see with this example, if you satisfy the data requirement, this wave separation algorithm will give you a satisfying result as well. But what if we do not satisfy the data requirement, which is always true for the real acquisition today? You may do not have the derivative of displacement to compute the traction T. So can this algorithm still be useful? It doesn't need to be perfection, just to see whether it can be useful, can be effective. So from this perspective, we like to show you a simplified algorithm we developed to reduce the requirement of traction corresponding to the limited onshore acquisition today. Next, I'd like to use a 2D case to show you how that idea arrives, but this method is extendable to 3D as well. This is a land data experiment. You have an air half space, and then the Earth's half space with heterogeneity. The source is a force vector acting on the air-Earth boundary like a Weber size. And the receivers are right beneath the air-Earth boundary. It measures the displacement along different directions. This is a conventional onshore acquisition. Now I'm going to put several approximations onto this experiment. You will see with those approximations, the data requirement can be significantly reduced. Now first, we use a vacuum half space to approximate that air half space. Therefore, you have this vacuum over Earth model. And second, we assume that external force F is local, and it can be expressed as a time function by a spatial delta function. F is known as the source wavelet. This is a very reasonable approximation because the size of your Weber size track is very small in comparison with your entire exploration region. So now with these two approximations, we will have the boundary condition says that along the vacuum Earth boundary or along your acquisition surface, traction equals to 0 everywhere except at that source point. It equals minus F by a spatial delta function. Now let's input this boundary condition to that wave separation algorithm we saw earlier. You will see the second integral turns out to be a product between that external force and this analytical Green's function. Therefore, we have this simplified algorithm. Comparing these two formulas, you will see that instead of requiring traction everywhere along the acquisition surface, that external force information or an estimated source wavelet is enough to compute the second term. This is what we mean of reducing the requirement of traction by a simple source wavelet with this simplified algorithm and a vacuum Earth approximation. That that source wavelet information can be estimated by the base plate, for example. So now you may ask, can this vacuum Earth approximation produce some useful result? Say we generate the data from air over Earth, and then we substitute the data into that simplified algorithm and process that as if it was from vacuum Earth. Can the result turn out to be useful? If yes, this approximation will be practical or valuable. Next, I'd like to numerically examine this assumption following the way in this red box. We use a similar model here, and you have an air half space and then two layered Earths with parameters listed below. And this time, the source as a vertical vector is acting on the air-Earth boundary, and Fz is assumed known, and it is a time function. And in addition to that, the receivers are right beneath the air-Earth boundary. At this time, we only generate the displacement ux, uz, and we assume we do not have traction anymore. So next, let's input Fz, ux, uz to that simplified algorithm. Hopefully, we can get some good result. Okay, so next, I'm gonna only show you the wave separation result of the vertical displacement. With this model, with this air over Earth model, you will have this total uz as shown in this slide. You can see the relay wave actually dominates the energy, and in addition, you have these different primaries. They are interfering with the ghost. That is because the receivers are right beneath the air-Earth boundary, so the outgoing primary and its ghost have the same travel time. And you have different PS events, PS combination here. Now let's input this data together with UX and FZ into that simplified algorithm, which assumes a vacuum Earth model. You will have this result. Flip back and forth, you can see the majority energy of the relay wave is reduced in your output. There is a residue, but the energy here is really very weak. In addition to that, these three events include both primary event and the ghosts. Their amplitude will be ordered in the output. That is because there are no ghosts anymore. So to further evaluate the accuracy of these predicted primary or the outgoing reflection data, I will show you the primary which is generated by using their analytical forms as shown in this slide. So this one actually provided you the ground truth result. Let's compare this most accurate primary with the primary predicted by using that simplified algorithm. You will see their amplitude match very well. So it means that the ghosts have been effectively separated out from the data, and the primary event is returned without injury. Now, so from this example, we assume that the world is composed by vacuum over Earth, which is not true because the input data is generated from air over Earth. Given all that, this simplified algorithm can provide us this extremely encouraging result and without needing traction anymore. Let's draw the conclusion here. We first remind you when you satisfy the data requirement, then Green theorem wave separation method can give us a satisfying separation result. It can separate the ground roll and the ghost without damaging the reflection data. And further, considering the traction requirement is not easily to be satisfied everywhere today, we make approximation that that air over Earth is actually vacuum over Earth. And with that approximation, we derive a simplified algorithm. It reduces the requirement of traction to be a simple source wavelet, but still provides the usefulness and the effectiveness. In the near future, we'd like to further investigate how this algorithm performs with less than full data component. For example, you may only have the vertical displacement, how this method will perform. We'll tell you we'll keep you posted in the future. Okay, the third topic is that we extend the wave separation method to ocean bottom for deghosting. It's well known that the destructive interference between the upgoing wave and the downgoing wave, which is the ghost, can lead to notch in your amplitude spectrum. Well, at the near offset, the first non-zero notch can happen at a frequency of c over 2z. C is the water speed, and z is the cable steps. So the deeper the cable steps, the lower the frequency the first non-zero notch can touch. Here is an example. If your ocean bottom data is at 150 meters, the first non-zero notch can come at 5 Hz. So your data spectrum starts getting influenced by the ghost notch since very low frequency to high end. people invest a lot at ocean bottom in order to get a better information about the reservoir. For sure, deghosting is extremely important. It can provide us the broadband data for amplitude analysis, and the boosted low frequency is significant for many applications, including migration and inversion. So in addition to that, to better deliver the promise of inverse scattering series, multiple removal methods, and stored C3 imaging method, deghosting is an essential prerequisite. Well, Green's theorem can be extended to the ocean bottom to remove the ghost from both the pressure data and the multi-component displacement data. Instead of showing you how that extension is achieved, we just show you the deghosting result of your multi-component displacement. But keep in mind that in order to deghost either pressure data or the multi-component displacement data, we need both of them as input. Okay, this is a model we use here. We have a water layer and two layers. Parameters are showing below. With this model, we will generate both the pressure data P and the displacement U here. P is generated slightly above the ocean bottom in the water, and displacement is generated slightly below the ocean bottom in the earth. Now let's input P and UX, UZ to the wave separation algorithm or deghosting algorithm. We can get the receiver side deghosted displacement. We only look at the vertical direction here. So now with this model, we can get this total UZ. This is your input data. Now applying the deghosting algorithm, you can get this upgoing UZ as shown in this slide. So this is your input data, and this is your output data. You can see that there are some events with particular strong amplitude existing in the input data, but not in output. We can point them out. 1, 2, 3, 4. You have these 4 events exist in your input data, the total pressure data, but they disappear in the output. So what is the meaning of them? We can show you their repass plot as shown on the top of this slide. You have the free surface, you have ocean bottom, and this is the measurement surface where the displacement is measured. We put the measurement surface slightly below for clarity, but actually the measurement surface is right beneath or at the lower boundary of this ocean bottom. So for all these 4 events from top to bottom, we will show you the repass plot from left to right. Okay, you will have this direct wave, the wave with 1-time reverberation in water, 2-time and 3-time reverberations in water. Then all of them will be collected by the receivers right after they transmit into the earth layer. You can see all these events are actually downgoing, and they do not experience the earth's reflections. But if we compare these 4 events with the other events that do experience the earth's reflection, these 4 events have particular strong amplitude. However, our interest is to obtain those events that come from the Earth, because the useful information, specifically the potential hydrocarbon information, could be there. After deghosting, this trouble can be solved because all these 4 events will be separated out from your result, and all the left events are coming from the Earth, and they take the Earth's property information and they are going up. So now we have shown you these 3 progress within the Green's theorem preprocessing. The second part of my research is related to the inverse scattering series internal multiple attenuation. We look at the performance of this algorithm when the Earth is inelastic, where the absorption and the dispersion exist. We will show you some result in this afternoon. Thank you.